Properties of transition metals. Especially in 1A, we talked a lot about main group elements and how they were predictable and they had different patterns and things. And we kind of just skipped over the transition metals. And they said, well, these are the trends for the main group, and then there's those guys in the middle, and we're going to ignore them. So now we're going to pay a little attention to them. In some ways, the transition metals, and remember, those are the ones with the d orbitals here in the middle, the sunken down part of the periodic table. Those transition metals, in some ways, are very similar to each other, especially when you look at the properties of main group elements, where you've got very reactive metals, you've got very reactive gases, you have rather inert nonmetal solids, just a lot of variation. The transition metals are all metals, right? And other than mercury, they are all solids at room temperature. And so in some ways, they're very, very consistent. They have moderate to high densities. They're good conductors of electricity. They have high melting points, and they have moderate to extreme hardness. And these similarities are due to similar electron configurations. As we're going across the row, it represents the filling of the d orbitals. And yet, each of these elements is also unique, and they have a wide variety of chemical behavior. So let's review electron configurations. Electron configurations, we talk about the 4 quantum numbers. There's the principal quantum number, integers 1, 2, 3, 4, principal energy level. And then we have the second quantum number, which corresponds to sublevels, S, P, D, and F. And then there's another quantum number that specifies the specific orbitals. And so there's one s orbital. Each orbital can hold 2 electrons. There's 3 p orbitals. There's 5 d orbitals and 7 f orbitals. And there's a particular order of filling that we can actually read off of the periodic table. When we get to the transition elements, of course, today would not be a day when my husband left his laser pointer in here. That'd be too convenient. But as we're going across the periodic table, hang on just a minute. Okay, so I pulled in a periodic table. So these blue parts of the periodic table correspond to the 2 s electrons. The p electrons, 6 of them are over here, and d. These are the transition metals, and so as we're going across here, for the most part, we're adding 1 electron to the d orbitals, the d subshell. Now, this is 1s, 2s, 3s, 4s. So the period number corresponds to the principal energy level for the s and the p subshells. But the d subshell, this is actually the 3d subshell. It's n minus 1. So here n is 4, this is going to be 3. And the way I think of that, I'm pulling out my intro chem tricks here, this looks like a stair step to me. And it should just go, it should go down here, not down there. And so I think of this as originally being up here, and there was like a sinkhole or something, and it sank down, right? And so this is 3, but it sank down a level. So, you know, that helps some people. So anyway, so we've got the d orbitals being filled here. And so these have very similar electron configurations. Most of them have the 4s orbital full, and then they just vary in the number of d electrons that they have. Now, what was on that slide that we still need to talk about? So in the first 2 rows of the periodic of the transition elements, the electron configurations follow this pattern for the most part. Whatever the previous noble gas is, ns2 and n-1d x. So x can be 1 to 10. In the 3rd and 4th rows, we've got the noble gas, ns2, but we also have a filled f sublevel, and then the d's. So let's go to the periodic table and look at that. So here's our first row of the transition elements, second row of the transition elements, third row, there's this little gap here, right? And it goes 57, 72. That's not how they taught me to count in kindergarten, right? What happened to 58? Well, 58's down here. Really what we should do is take a pair of scissors and cut the periodic table, slide this apart, and bring this up in here. And it would go 57, 58, 59, etc. across 71, and then that would hook up with 72. Okay? Why don't we do that? My theory is it's way too long. The aspect ratio is wrong. It doesn't fit nicely on a piece of paper. It doesn't fit nicely on a screen. We don't use these guys very much anyway. So we just pull them out and stick them at the bottom. But after lanthanum, which the lanthanides are named for, after lanthanum, the 4F subshell fills up. And so for this third row of the transition elements, they have a filled 4F level. This is n-2 because just like the d orbital block has sunk down, the F also sank down. And so this is filling the fourth F subshell, even though it's in period 6. That should be a review. Okay, so these guys are have F orbitals filled up with electrons as well. There are a lot of exceptions, and the reason there are so many exceptions is because for example, the 4s and 3d sublevels are very close in energy. So moving an electron from one to the other isn't a big deal. Two notable exceptions in the first row are chromium and copper. And what we have with chromium is we have a half-filled 4s subshell and a half-filled 3d subshell. And there's a bonus, an energy stability in getting it half full or completely full. And what happens over here with copper is by moving one of the 4s electrons into the 3d subshell, we can completely fill that up. I have an analogy. If you want to hear it, you can go back and listen to my 3A or 1A videos, but I talk about the electron hotel. And the D subshell is a room with 5 beds in it, and each bed can hold 2 electrons. And there's like this coupon thing where if you have 10 people in the room, you get a discount. And so even though that room costs more, with that discount, it's still overall cheaper to bump somebody up into the room. And there's a coupon for the half-filled stuff too. So we see some of that going on. We just need to be aware of it. We don't have to freak out about it at all. When these transition metals lose electrons, they lose them from the ns orbital. They do not lose them from the n-1d orbital first. Let's look at the periodic table. Here's chromium. See, vanadium is 4s2, 3d3, and we would expect chromium to be 4s2, 3d5. But instead of doing that, it moves one from the 4s up to the 3d so they can both be half full. And the same thing happens over here with copper. Now, when copper becomes an ion, it's not going to lose the 3d electrons. It's going to lose the 4s electron first. And that's what all of these guys do, is they'll lose the 4s electrons first before they start losing the 3d. So let's write electron configurations for the ground state of osmium and niobium 2+. Okay, so osmium, we can remember that. Let's go back to the periodic table. Where's osmium? Right there. Yeah. So let's pretend that we don't have the answers right there. So osmium is, we're going to start with xenon, the previous noble gas. So it's xenon plus, this is 6s2, and this would be 4F. Those are all going to fill up, and we're coming over here. We've got 1, 2, 3, 4, 5, 6. We're going to get 6 in the 5D. Question?
Okay, so we have osmium, and then right above it is whatever that thing is. Why are those ones different? Why is the other one full and extra one as well?
Because it's one of the exceptions.
Lovely.
Yes. Yeah, ruthenium we would expect to be 5s2, 4d6. And that's not doing a half full thing with the d electrons. It's half full with the s. Off the top of my head, I can't explain that, but I know there is an explanation. Yeah. So for osmium, which always makes me think of Donnie and Marie Osmond. Osmium is xenon, so we put xenon. That means the electron configuration of xenon, and we're just going to write what comes after it. So here we've got 6s2, and then we've got 4f14, and then 5d, 1, 2, 3, 4, 5, 6. So that would be the ground state electron configuration for osmium. Any questions? Yes? Where does the 14 come from? That's a good question. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It's the one row. There are 7 f orbitals, and they each hold 2 electrons. It goes 1, 3, 5, 7. They're odd numbers, and then they each have 2. So that's where we get the 2, 6, 10, 14 business. Good question. Anybody else have a question?
And the 4 comes from the row?
These large numbers come from the period that the element is in. So for S and P, the number of that's the principal energy level, the highest principal energy level that is occupied. For S and P, it's the same as the period number. For F, it's the period number -1, and for F, it's period -2. And my non-scientific explanation for that is because they sank down, they fell down a level. D is -1, F is -2. Did I say it backwards? I probably did. I said F twice. I don't even know what I'm saying. Yeah, it's n-1 D, however many. For F, it's n-2. F, we'll call it Y. Y can be 1 to 14. Well, it could be 0. X could be 0 to 10. So how about niobium 2+? Well, anytime you're doing an ion, you want to start with the atom. NB, where'd you go? NB. There he is, number 41. So, 5th period. Previous noble gas, end of the 4th period. Krypton. Kr, krypton. And then after krypton, we're going to period 5. So we're going to have 5s2. And then, do we go into f orbitals or not? No, we don't. And that can help. If you look at the numbering, it's consecutive. 37, 38, 39, 40, 41. There's no jump. We don't have to go over to these guys, because those don't come in until the 3rd row of the periodic of the transition elements, which is row 6. So then we find out, well, how many spaces over is NB? I lost him already. He's 3 spaces over. 1, 2, 3. Right? So that's going to be 4D3. 43. Which is very close to 42, which is the answer to life, the universe, and everything. So any questions about getting the electron configuration for the atom? Now, for the ion, the 2+ charge tells us that it lost 2 electrons, right? It's going to lose these 2 electrons first. Those are valence electrons. Valence electrons are the highest occupied principal energy shell, energy level, so 5. So we're going to lose those. It turns out for this guy, it's enough. So we're going to get krypton 4d3, or you might also see this as krypton 5s0 4d3. Just depending on who's writing the exam. Yes?
Refresh me as to why we're not worried about the p orbitals that we passed through.
Why aren't we worried about the p orbitals?
They're included with the...
They're included in the noble gas. Yeah, so this krypton is 1s2, 2s2, 3s2, 1s1, I'm sorry. Yeah, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Krypton.
That's right, that's right.
Yeah.
I forgot about that. Oh, that's right.
It's kind of like, singing Mary Had a Little Lamb or something. Okay, so either of these are acceptable electron configurations for the ion. And just, throwing in some review. Well, actually, we couldn't do that. Never mind.
Do what?
Well, I was going to say, what are these isoelectronic with? But they're not isoelectronic with an atom because they're transition metals and they're losing the 4s or the 5s before the. Never mind. Blot that part out. Okay, so let's look at some of the trends. We studied these in 1A for the main group elements, and we're going to look at how they're different for the transition elements. So try to throw some review in here as well. So atomic size, to refresh your memory, for the main group elements. As we go down a group in the periodic table, the atoms get larger. This makes sense because, if we're comparing helium, it has 2 electrons in the first energy level. If we compare that to radon, that has electrons in the 6th level. Each of those principal energy levels gets larger. So as you go down a group, the atoms get bigger. What is a little counterintuitive is that as we go across a period, the atoms get smaller. And so if we compare sodium and argon, argon is actually smaller than sodium, even though it weighs more and it has more protons and more electrons and more neutrons. And the reason for that is effective nuclear charge. So if you're going across a period, sodium, magnesium, aluminum, etc., to argon, we're adding electrons in the same principal energy shell. And so the effective nuclear charge is increasing because we're also adding a proton to each nucleus. But there's shielding from the core electrons. The core electrons are staying the same. And so the effective nuclear charge increases. Higher charge between those valence electrons and the nucleus causes them to be pulled in closer. And so as you go across, they get smaller. So what we see with the transition elements is as we go across a row, after the first 2 elements, there's not much difference in size. And so we've got graphs here. So for the first 2 elements, there's a big drop in size. And then after that, there's some variation here, but there's not really a trend as we go across here. Yes?
Why is the 3rd row so much better?
Why is the 3rd row so much?
It's just much more pleasing to dot. It doesn't have as much variation.
That's a good question. I see it has a nice smooth curve. And green is a pretty color, but I like red and blue too. I don't know why there's less variation. Perhaps because they're a little bit, I don't know. I really can't speculate on that. But the reason that from here to here, we don't really see a trend in size. It goes down a little and comes back up again. That's not the trend that we see with the main group elements where it's just going down, 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 down. The reason is that as we're going across here, the number of electrons in the outermost principal energy level is nearly constant, right? They've got, in the first row of the transition elements, they've got the 4 s electrons. And as we're going across, we're adding d electrons, but we still have 2 on the outside, right? The effective nuclear charge ends up being relatively constant because we're adding a proton, but we're also adding a shielding electron. And so there's not a lot of difference in effective nuclear charge. We don't see much difference in size either. Going down a group, from the main group elements, we expect that the size will get larger as we go down. And so we do see that from the first row to the second row, there is an increase in size. That's expected. But then from the second to the third, these are just twisted around with each other. You can't really say that one is larger than the other. They're essentially the same. That's weird, because the third row has a lot more protons, neutrons, and electrons. Why isn't it bigger? It's got higher energy levels. So what's happening there is between the second and third row, we've added a subshell of F electrons. And it turns out that those F electrons do not shield effectively. So even though they are in there, they don't really count for the shielding. And so because of increased effective nuclear charge, the third row elements are about the same size as the second row elements, because the higher effective nuclear charge pulls those 6 s electrons in more to the size of the 5s. And that's a phenomenon known as the lanthanide contraction, that those 2 rows are about the same size. Any questions? Ionization energy. Do you remember what ionization energy is? The energy to do what? To ionize, to pull an electron off and make an ion out of something. So with the main group elements, we see an increase in ionization energy as we go across the period from left to right. Which, this isn't a scientific explanation, but if you think about sodium, sodium is a metal. Metals tend to form cations by losing electrons. When sodium loses 1 electron, it gets a noble gas configuration. And then you compare argon at the other end. What motivation does argon have to give up an electron? None. In fact, it is very motivated to keep all of its electrons because it has arrived. It's got that stable configuration. So that's how I remember that. So for the transition elements, as we go across, we do see an increase in ionization energy, which is what we expect. Going down a group in the main group elements, what happens to the ionization energy? Does it go up or down? It goes down because the atoms are getting larger and larger, and the distance between that outer electron, that's the one that's going to be pulled off, and the nucleus gets larger. And Coulomb's law tells us that the force of attraction drops off very strongly as you increase the distance. What happens with the transition metals is we see an opposite trend. The third row actually has a higher first ionization energy than the first 2 rows. And we see that the first 2 rows are roughly equal, and then the third row's higher. Why? Well, no, they're not really much bigger. The charge of the nucleus is larger. The charge of the nucleus is larger. Atomic size is similar. Do you remember Coulomb's law? No. Coulomb's law tells us that potential energy is proportional to Q1, Q times 2Q, over the distance between. So the attraction between opposite charges or the force of repulsion between like charges. will depend on the magnitude of those charges and how far apart they are.
Okay, yeah.
So if the distance is the same, but one of these charges gets larger, then the force of attraction is greater. And then it's harder to pull off an electron. And so the result of this increasing charge but similar atomic size is that those outer electrons are held more tightly. Ionization energy increases. Electronegativity. The way I think of electronegativity, it's the attractiveness that an atom has for electrons in a chemical bond. And fluorine is the most electronegative, and so as you're going across a row, as you get closer to fluorine, electronegativity increases. If you're going down a group, you're getting further away from fluorine, electronegativity decreases. The noble gases aren't included in there because some of them form absolutely no compounds, so how do you measure electronegativity? And the others hardly ever do, and so we just leave them out. So what we see, here's this trend, as we go across, we see electronegativity increase. That's expected. But going down in the group, we see the opposite trend once again. We see an increase from the first row to the second row, and then no change for the second row to the third row. And the trend is the opposite for main group, that the electronegativity would go down with each successive row. And again, this is due to the same thing that the ionization energy trend is due to. Relatively small size change with large increase in nuclear charge. So if you look at tables of electronegativities, gold is the most electronegative metal. It actually has an electronegativity of 2.4. It's more electronegative than phosphorus. It's up with carbon. And so compounds with a negative gold ion, a gold anion, have actually been observed. That's not something we would expect from a metal, right? We told you that metals form cations. No, it doesn't make it. Think of it this way. All the other guys, they're just forming cations, right? And so this guy's more in the middle of the road. It'll form a cation, but it'll also form an anion. You think about carbon. Carbon's pretty stable, right?
Yeah.
And
it reacts with a bunch of stuff.
It reacts, but it's not like sodium or chlorine or anything.
Highly reactive.
Right. And gold does form compounds, but it's not very reactive. But it can actually go kind of either way. Any questions about electronegativity? Oxidation states. We've learned that transition metals exhibit a variety of oxidation states. Most of them can have more than one oxidation state. And these range up to +7. So the highest charge on an ion, the highest oxidation state is +7, and that's for manganese. Look at manganese in the periodic table. Right there. So it's 1, 2, 3, 4, 5, 6, 7. It's got 4 s electrons, 2 of them, and then 5 of the 3d. If it loses all 7 of those, it becomes isoelectronic with argon. And when we looked at the main group metals, we used that to explain, well, why does aluminum form a +3 ion and only a +3 ion? Because by losing 3 electrons, it becomes isoelectronic with a noble gas, and that is more stable, and so that's why they do that. We'll look at this in the chart on the next slide in a minute, but if we look at metals that are to the left of manganese, let's just call it manganesium and get it over with. Metals to the left of manganese, their highest oxidation state will be one that gives them a noble gas electron configuration. And if we look to the right, we see that those metals have lower oxidation states, generally +2 or +3, which corresponds to losing the 2 s electrons. So they lose those, and that gives them a +2 oxidation state. So this looks like, you know, somebody playing tic-tac-toe or some such game. So here we have oxidation state versus the first row transition metals in order. And we see this definite trend here. So here's manganese. Let's draw on this. If we think of the periodic table, these would be S electrons, and these would be, the D, right? And so scandium, all of these guys are, for the most part, are going to have 2 S electrons, and then scandium has 1 3D electron. So if it loses the 3D and both of the S's, then it's got a +3 charge, and it's isoelectronic with the noble gas before it. Titanium has 1 more electron, so it has to get a +4 to get down to that. And we're talking about argon here. Vanadium will do a +5, chromium a +6, manganese a +7. That's the highest oxidation state. Because to take any more, to get a higher oxidation state, then you'd have to break up a noble gas configuration, and that's not going to be easy to do. These also have the oxidation states below. Now, there are some that are less common and some that are more common. And so, you know, we see iron 2+ and iron 3+ a lot, but there's also 4, 5, and 6+ for iron. But most of these that are to the right will be either a charge of 1 or 2, and these guys sometimes 3. So there's trends in those oxidation states. Any questions?